Hi everyone, I hope that you're all doing well. In this lecture, I want to give an overview of what we've gone over in the last few lectures, really beginning with sampling distributions. So the binomial distribution is the first example of that, then moving on to distributions of means, and then two important things that we do with them, hypothesis tests and confidence intervals. This is really the key to inferential statistics as opposed to descriptive statistics. So in other words, drawing some kind of loose conclusion about the population as opposed to simply figuring out the best way to, say, represent the relationship between two variables in the sample without respect to whether or not that is a relationship that holds in the population. So, for example, a kind of classical case of descriptive statistics, technique that we talked about at some length and derived in a couple different ways would be the correlation coefficient or Pearson's correlation coefficient specifically. But something like a hypothesis test or a confidence interval would be a kind of canonical case of inferential statistics. So I want to summarize these latter techniques before we move ahead a little bit in their use because they're very important. So here's the logic. Even if a variable's distribution is skewed, the distributions of some key properties of it, so counts of successes on a dummy, means or proportions, across all possible samples look normal. This is the central limit theorem. We can use this to do inference on a population parameter. So if we're within plus or minus some critical z standard deviations of the mean c% of the time, then x bar plus or minus that critical z times the standard error will include mu c% of the time. So that's a confidence interval. And again, just to break down these parts, and sorry for the minor typo here, there should be another parenthesis there. This is the sample mean. This is some number of standard deviations on the standard normal, but also on any normal. So this might be something like 1.96. It might be something like 1.64. It might be something like 2.5 and change, etc. This then would be hard to generalize about because it'll vary from sample to sample. But for instance, if you happen to know that you had a sample of exactly 10,000 people, and then you had a, say, individual standard deviation on the variable, so the population distribution of the variable were something like, let's say, 500, then the standard error would be 5 because you would have 500 over the root of 10,000, which happens to be 100, pardon me. So then the division would then be 5, just to give an example. But again, that's pretty arbitrary. We can also kind of go in the opposite direction, although doing basically the same procedure, just in reverse. So if we picture the sampling distribution under some null hypothesis, so we postulate a value for mu, then we take a z-score using x bar, we can get a p-value for results this weird or weirder in that case, and that's known as a hypothesis test. Kind of incidentally, the binomial is a special sampling distribution that is useful, but can also be derived by hand, making it feel more accessible. We won't actually use the binomial a ton in practice, but it's kind of nice to just be able to see that you can come up with these things by hand and that they're very, kind of tractable at the simplest level. So I wanted to look at this logic laid out in pictorial form. So on the left, you see the binomial distribution illustrated, and then on the right, we'll see the generalized central limit theorem. Here's the big idea of the binomial distribution one more time, and this is the same idea as behind the central limit theorem generally. It's the case that we have more information if we think about a collection of observations as being one large sample rather than a bunch of individual samples of smaller size, possibly as small as size n equal to 1. And then we think about group level properties of that larger sample, such as the mean or the sum of successes, or in other words, just the total, if it's a dummy variable. And we always are considering the individuals to be draws from a dummy variable when we talk about successes. The idea is that we have additional information about that variable's distribution across many possible samples, or at least some properties of it, than if we were to simply consider it to be, a bunch of draws of size n equal to 1. That might sound kind of confusing or backward at first because you might not even consider this initially, but this is something that when people learn the central limit theorem, they very often think. they very often think that they need to replicate the sampling distribution on their own at home. So if they have, say, a sample of 500,000 people, they tend to think, oh, okay, well, now what I can do is decide whether or not I'll have, say, 5 replications of size 100,000 or 100,000 replications of size 5. And size means sample size here. And the point is that we don't have to make that choice. That's not something that we actually have to do, because we can just know that probability theory tells us that these means and counts or successes are taken from these normal distributions. So we can just use our sample size and we can kind of use that maximally. So in other words, we can say, sorry, clicked out here. We can say that if we have a sample of, say, n equal to 500, it's drawn from this sampling distribution. It isn't actually, and in fact, we're throwing out a lot of useful information if we consider it to be, 100,000 replications, or sorry, 100 replications of size n equal to 5 or something like that. So that's kind of a key point about the central limit theorem. We don't actually have to rebuild these sampling distributions on our own. If we did have to do that, a lot of statistics would be sort of pointless, at least before the last few years. It has become much easier to simulate building your own sampling distribution with a procedure known as bootstrapping, but it's not magic, the bootstrap, and it's also only become possible in relatively recent years, and its theoretical properties are still being worked out in a lot of cases. So what we want to do instead is just kind of learn the robust underlying probability theory, which doesn't require us to do any of these fancy computer replications. We proved with theory, sorry, I'm just kind of adjusting my computer here. We proved with theory in the case of the binomial distribution that this is what the distribution of sample successes looks like across many different replications. Here you can see that generalized for means. So in this case, I again simulated something that we already know to be true by theory, which is that even when the variable's underlying distribution is skewed, so here we observe income for all Springfield workers, some large city of size 200,000 that is really just the CPS, but I'm calling it Springfield. But you might have an interest in a population that is as small as 200,000. There's nothing wrong with that. So we can treat the CPS like our population and then sample from within it. In this case, I subsampled 10,000 people. So not a giant share, but fairly large. And then I did that 5,000 times. And so then I just plotted all of the means here, and you can see that the true population mean, in this case, happens to be the mean of the sampling distribution, which is true according to theory, up to a rounding error because I couldn't infinitely simulate this, but this proves the point. And the distribution of sample means is, of course, very close to the normal approximation here. And if we did this, this is a simulation, so the law of large numbers actually tells us that if we did this over and over again, and we made the sample larger and larger, then this would become asymptotically true. Here, it's clear enough from a large sample and a large number of replications that it is true, and we know it to be true by theory. So what do we do with these things? Again, what you could do is use a, say, confidence interval to try to make a guess about the true population mean. Here we have a situation, I know I showed kind of two versions of this. So what this represents here is a bunch of possible worlds that could exist when we construct a confidence interval. The true population mean might be 46.75 or 46.3 or 89, it's hard to tell there, or 47.19 or 47.66, one of these things. We can't actually say for sure, and that is, frustrating, right? But what we're hoping for is a situation in the long run where we capture the true population mean in its bounds some C% of the time. And these all represent situations where that would be true. Now, we would expect that 1 minus C% of the time we will miss the true population mean. Here, because this is a 95% CI, if you work out the binomial probability, it makes sense to show 4 of the 4 as being successes. Now, we don't know which of the ones is reality here, but the point is that we can still make a pretty good guess about what the true population mean mu is, and the idea is that the same confidence interval, so these are all you can see that the sample mean is always the actual sample mean in each of these pictures. It'll change position relative to the true mean mu, but the idea is that we capture that true mean mu in there in most cases. Here's the logic of a hypothesis test. This is from our example with the number of pets. And this is, kind of a slightly different example here because I pulled the standardized sampling distribution. But the idea was that this is the conclusion of our two-tailed test. Recall that our sample statistic, when we actually observed it, ended up having I think the number was 1.72. When we standardized it, we found that the actual z-score was 2.44, and then we could calculate the associated probability of a sample statistic that weird or weirder. So in other words, the probability of a z-score that larger, or its additive inverse, the negative version of it, that small or smaller. And we noticed that when we added up that area under the curve, which we could do at table A or theta, it was below a cutoff probability known as alpha, and that's represented geometrically by this rejection region. This rejection region is alpha. It's geometric, so we call it a slightly different thing. I know the proliferation of jargon is a little bit frustrating. Anyways, that's what the logic of a hypothesis test is. So we were able to say that we have a fairly strong case against the claim that the mean of pets in that particular example was 1.5 pets per household based on the sample data. So I wanted to run back through the binomial in some greater detail because I do think the computational details are worth knowing. So what does it do? It gives us a model for how probable any possible number of successes k is given a sample of size n. Remarkably, the binomial probability mass function, so just the binomial distribution, which is it's a mass function basically, looks more and more normalish as n grows. And remember that n here is the sample size. It's not the number of replications. And by the way, you should check out my footnotes if you don't normally, because there's oftentimes useful things in there. So in this case, note that, strictly speaking, there are no replications needed. So we don't actually have to do any kind of replication whatsoever. We can just say, we know we have a sample of this size, and that's it. There is no concept. There is no place in the binomial distribution to write down some number of replications. It's a non-concept. All it, the connection to many replications is just that we know basically that this distribution, governs the selection of, any number of possible samples. Like there's, you could basically spit out the distribution of all possible sample counts any number of times that you want by using the binomial distribution, but it is not like an operative concept in the distribution itself. Okay, so why am I making such a stink about that point? Well, the power of the whole theorem is that we only need to do one replication in practice. So we only need one sample to be able to say a lot about our data, and if we happen to get additional data, we don't consider that two replications, we just consider it a bigger n. Again, I've just gone through this experience before teaching this class and realizing that this concept really sometimes doesn't connect for people, but I'm showing you a lot of simulations that are not things you have to do, and they're not things you should be replicating. They're just things that are meant to illustrate the point that the theory works. So in retrospect, now that we've learned what sampling distributions are, we can say that the binomial distribution is a sampling distribution. So that's an important fact. So why is the formula written the way that it is? And you'll note here that I'm going to again use the slight notation change of using pi in place of little p because I think it's actually less confusing than having little p around. So the binomial distribution has a probability mass function that is this. It says that the probability that the random variable x, which we use to denote just the number of successes in a general sense, being equal to some actual realization k, so say 10 or 20 and a sample of size 100, is equal to the following. It's equal to n choose k times the probability of success on a single trial to the k times the probability of failure on a single trial, which logically has to be 1 minus the probability of success to the n minus k. N is our sample size, k is the number of successes, pi is the probability of success on one trial. So what do all the components do? Well, n choose k, let's actually start with this. I usually find that is more intuitive. So the probability of any particular sequence of k successes is given by pi to the k, because we assume that all of the subsamples, all the individual trials, are independent of one another. So their probability in that case happens to conveniently just be the probability of each one multiplied by the probability of all the others. And I said that in a way that could leave the door open for some ambiguity. So you just multiply, very simply, nothing complicated. You multiply all of the individual probabilities. Then you just do the same thing for the probability of failures, right? So we don't just have successes, we have failures in almost all cases. So you need to find the probability of the whole sequence. But then the thing is that you don't actually care in any case that we would deal with about the probability of some particular sequence of successes and failures. What you care about is the probability of some number. So how do we add up how many trials could be successes from a set of n total trials? Or in other words, let's not use the experimental language so much. So how many ways could k subjects be successes when we have n subjects overall? And that just happens to be given by n choose k, which is the binomial coefficient, hence the name for the distribution. And that generically gives us the number of ways of forming k distinct groups from a set of n items. Distinct groups of size k. Sorry for saying that in a slightly inaccurate way. So it tells us how many ways we can form groups of size k from a set of size n. And notably, because we are choosing k successes but also n minus k failures, that means that n choose k must be equal to n choose n minus k. They would have to be symmetric, and that's actually a fact I've shown in the class. You can work that out with algebra. Just recall what the actual formula for n choose k is, and then whenever you see a k, plug in an n choose k, and you'll find that the algebra is very simple. So those happen to be the same. And recall finally, although I said it aloud, that big, bold P or blackboard P is the binomial probability. These are totally separate concepts here. Pi is the probability of success on a single trial, but big blackboard P is the probability of observing a sample with k successes. So just make sure to keep those separate. Some other important facts about the binomial distribution one more time. The mean of the distribution is n by pi. That's pretty intuitive. The variance is n by pi by 1 minus pi. That's also pretty intuitive. The reason for this fundamentally is that we have a sample of size n. We have the probability of pi that any trial will be a success. So we just, the best guess we would have at the number of successes is the size multiplied by the probability of a success. Super intuitive. There's a formal proof in the appendix, but I really don't think it's worth consulting in this case, to be completely honest. Use your intuition when you can. The variance is also quite intuitive. So it happens to be the case that when we add up n random variables that are all independent, their variances just simply add. And so we learned before that the variance of a dummy at the population level, and by the way, this is a population distribution, not a sample distribution. So sampling distributions are population distributions, basically. It's a slight abuse of language to even say that, I guess, but you can think that a sampling distribution is a known theoretical object, so it's a population in that sense. So anyways, the variance is then simply n copies of these individual random variables, which have a variance of pi times 1 minus pi. So how does it work in practice? Well, recall that we actually rarely know pi, and that's usually something that we actually want to know about. So instead what we do is we postulate a value of pi for a sample with fixed n and k. And the reason we do that is that what we probably do have information on is a sample with fixed n and k. We observe the sample, and we just immediately can see what n and k were. For example, if we have a sample of, say, 100 people, going back to our example from before, and we're interested to know the probability of, in, let's say, a country that's experienced a lot of demographic change, are the probabilities of natal males and females basically the same as they were before, we could postulate that it's equal to 0.5 and then gather a sample where we happen to have, say, 60 females and 40 males, and then we have all the ingredients we need. We have a observed n, 100. We have an observed k, either 60 or 40, it doesn't make a difference, just pick one. They lead to the exact same conclusions. And then we have a postulated value of pi 0.5. And then what we would do is we would find the probability that the number of successes is equal to k given these two facts, pi and n. And I should, change that theta to pi, just notational change. And then we can kind of easily extend this to the case where we've got, say, the probability that the number of successes is less than or equal to some number or greater than or equal to some number. And the reason that we start doing that is that, one, it is necessary in the case of a continuous distribution, or in other words, when we have a random variable that can take on non-integer values, such as a mean. A count can't take on non-integer values. But also in a lot of cases, we're just interested in knowing what was the probability of something this weird or weirder given the null. We don't actually care that much about exact probabilities of numbers of successes or outcomes of this random variable, even though we can find those in this case because this is a probability mass function, not a probability density function. But again, we've been working with the normal and the normal approximation, and recall that very important fact that the probability of an exact value on a normally distributed variable, if it really is normally distributed, is 0. The area under the curve of a single point is 0. So that's an important point. So then what will we do with this type of information? Well, if p is very small, it's evidence that our guess for pi is wrong. So you should hopefully by now recognize that this is a form of hypothesis testing about pi. In practice, we often use the normal approximation to test those possible values. The binomial for more than 1k is computationally kind of taxing by hand. At a minimum, you should use theta. So you write display binomial nk pi, just like that. And again, pi and small p are the same thing in this context. It's just that I've found that people find that confusing. So let's look at an example. Let's suppose that we believe the population probability pi of high school graduation is 90%. The 2018 GSS, which has an n equal to 2347, and that gives k equal to 2086. So is that evidence against our guess for pi? Let's break down each component of our formula. I think it might be kind of instructive. So taking pi to the k times 1 minus pi to the n minus k gives the probability of some particular sequence of successes. So what does that mean? Well, what's the probability of, say, observations I equal to 1, 2, 3, all the way up to 2086 being high school graduates, which happens to be just the number of successes observed in the GSS. It would be pi sub 1 times pi sub 2 times pi sub 3, all the way to pi sub 2086. That's just this quantity here. But we didn't just observe 2086 people, we observed 2,347 people, so we need to get the probability of the whole sequence by multiplying 1 minus pi sub 2087, 1 minus pi sub 2088. This is, again, a slight abuse of notation because this is really the first failure, not the 2087th, but I'm just trying to show that we're keeping track of every individual. So the idea is that when we actually do out the math here, this would be a number of operations here. The number of factors in this product would be equal to 261, which is the difference between these two numbers here. So that's our n minus k, 1 minus pi taken to it. And then this would be 2086 factors here. So this is pi to the k. The way we write it implies that all successes come first in this case, but this is the probability for any specific assignment of individuals to success and failure in this context. So for instance, if you, say, started interspersing these people in, so you had pi 1 and then 1 minus pi 2, pi 3, 1 minus pi 4, etc., when you actually do out the math, it's just simple commutativity of multiplication. It comes to the same thing. So it's might as well, just write it out in this fashion here, which also happens to mimic what the binomial theorem looks like. So that's another reason to do it like that. This. Three, two, one. So we're still keeping track of basically these. No, one more time. 3, 2, 1. So the idea is that we ultimately end up multiplying the probability of represented, before we did the sample, the probability that every person had of being a success or a failure in the end. So we'll end up with a sequence, a product with 2,347 factors in just this fashion here. which is kind of like, we're basically accounting for everyone's probability before the sample was selected of this happening, this particular sequence. Now note that the way that we write it implies that all successes come first. So when we write out all the successes first, that's sort of implying that, this sequence has some kind of special meaning. It doesn't. It just happens to be convenient to, write this as pi to the k times 1 minus pi to the n minus k instead of like pi 1 times 1 minus pi 2 times pi 3 times etc. And again, we're going to ultimately end up adding up the probabilities of all the different ways of getting this sequence. And so what that means then is that it doesn't really matter at all what the probability, what the particular sequence we count the probability of is, because the probability of this number of successes and 261 failures, it doesn't matter what order they come in, that particular sequence has the same probability. So we just need to then add up that probability to take account of all the possibilities. So why do we multiply by n choose k? Well, it's just as I said, we're not interested in any particular assignment of individuals to success. We care about the probability of this number of successes given n and a possible value of pi. So n choose k counts the number of unique ways for k individuals of size of a group of n to be successes. So multiplying just adds up the probability of any assignment of k successes. And you can kind of see that here, right? So this is an example. It's a little bit busy, but I thought I might show it. So the idea is we've got a number of options. What we're doing here is flipping a fair coin 3 times. And at each step, we've got the number of options n to the k, right? And we figured that out before when we did a little bit of basic probability. So the probability of any particular sequence of length n is 1 over n to the k. So for instance, the probability of any sequence of, heads or tails is 1 over 2 to the 1 or 2. For any sequence of, 2, we have basically here 1 over 2 to the 2. And you can see that there's 4 options here, so any one of them has a probability of 1 in 4, if they're all equally probable as they are here. Then finally, if we come down to this last step here, where we got sequences of length 3, and you can kind of see how I got there in these cases, we would have the probability of any one of these, such as this, or this, or this, etc., is 1 in 8, right? And so then what we do is we can say, oh, well, conveniently, that's just p or pi to the k. I should have changed the notation here, but I was lazy because I didn't want to redraw the figure. So the idea is that counting up this probability, taking the probability of any particular sequence tells us this is the probability of one specific way of getting this number of successes and this number of failures, right? And in this particular case, I just happened to say we were interested in 1 success and 2 failures, and you can see that there's basically 3 ways to do that. And so that comes from 3 choose 1, which is equal to 3. So we have 3 options, and we can choose exactly one of them to be a success. So basically the idea is that could be first, second, or third. That happens to be really easy to calculate by hand, but if it weren't, you could do it that way with the formula. And then we just multiply out that 3 by the probability of any of these, any one of these successes. So we get 0.5 to the 3, which is 0.125, and then we would multiply that by 3, and we would get, you could do a little bit of mental math there, but we'll do, reflex. We'll do that, so we would say display 0.125 times 3, and we should get the same number back if we just divide 3 by 8, and indeed we get the same exact thing back because we see visually that 3 out of the 8 options represent this pattern that we're interested in. So note that we're using 2 different rules here that we learned before. We use the permutation with replacement formula to find the probability of any particular sequence. So that's this thing here. That's how we used that before. But then we use the combination without replacement formula to count all of those sequences. So here we can picture the exact sampling distribution with heights in red representing our probability of interest. This is obviously tough to draw by hand since it's not a smooth curve, but you can use the normal approximation. So let's look at two ways of doing this. We could either calculate the exact probability in Stata or use the normal approximation. To do this exactly in Stata, you would just use the syntax that we saw before. And again, we set up the problem before like we were just interested in the number of, basically the probability of this number of high school graduates or fewer, and this number is 286, or 2086, pardon me, in a sample of size 2,347 if the probability of a success is 0.9. And we can just calculate that in Stata. It happens to be 0.039. But here's how you could enter it into Wolfram as well. And note that in this case, the syntax is a little bit complicated. But the idea is that we want to go from k equal to 0 to k equal to 2086. And then we want to find the probability of 2,347 choose k times basically 0.9 to the k times 0.1 to the 2347 minus k. Basically, we do a whole set of separate binomial problems that will then kind of add up and turn into the probability of that number of successes or fewer. So we end up including 2086, but we start with k equal to 0. We can also use the normal approximation. So we can calculate the mean of this sampling distribution. It's equal to pi times n, which is approximately equal to 2,112.3. Standard error is just the standard deviation of a binomial variable. So we first find the variance, it's 211.23, and then find the root of it, which is 14.53. And our approximation is pretty good in this case. Note that we're off by just a very small amount here. We get a probability that is equal to 0.0351, and that is extremely close to what we got working by hand. So both of these are viable methods in this case. We can also translate this to a hypothesis test. So when we first learned the binomial, we hadn't yet used the language of hypothesis tests, but let's view this as a hypothesis test. So what was our null and what was our de facto, or just kind of actual alternative, given that we didn't specify a direction? So our null was that pi is equal to 0.9. Our alternative was simply that it's not equal to 0.9. And what that means is that we really should then double our p-value because we didn't actually know a direction. And you'll note here that we're right on the border. We could use our conventional cutoff of alpha equal to 0.05, but I think it's best to avoid that when you can. So what we would say here is that results such as these would be surprising under the null, since they're conventionally a low probability event, and that might provide some evidence against the null. Here's an example of an exact binomial problem, just for the sake of showing that we can sometimes solve these very easily by hand. So here's an example that's pretty similar to the one I mentioned before. If a family has 4 children, is it more likely that they will have 2 boys and 2 girls, or 3 of one sex and 1 of the other? Assume that the probability of a child being a girl is 1/2, and that the births are independent events. This is a less sociological example. The idea is that in this case, we have a sample of size 4. So this family is one draw from this kind of overall sampling distribution or binomial distribution with, in this case, a fixed parameter 0.5 and a fixed sample size 4. You can see the answer here visually. Hopefully you can kind of tell that there's this interesting fact that the probability that they'll have 3 of one and 1 of the other, so this situation or that, is obviously more probable than exactly 2 of each, which is somewhat counterintuitive, maybe not super counterintuitive, depends on your perspective, but we can show how to calculate that by hand exactly. So let x equal the number of girls born, let pi equal 0.5 given by the context, n equal 4. Then we find the exact binomial probability that the number of girls born is 2, and that happens to be 4 choose 2 times 0.5 to the 2, which is, in this case, this is the probability of a success to the k, and this is the probability of a failure to the n minus k. These just happen to work out to be the same here. And we get 0.375, and then we have the same thing for x equal to 1, and then hopefully you can also see that for x equal to 3, it's just going to be symmetric. So we can just double the second probability to get p of x equal to 3. So we have the probability of 3 of one sex, 1 of the other, is actually significantly larger. It's 0.5 as opposed to 0.375. So I now want to discuss confidence intervals. So remember that this is the logic of the recipe. This is why these work. So when we've got this table A, we have information about basically, we've got these inputs to table A. They're inputs to the normal cumulative distribution function. And those inputs are the z-scores, and the outputs, the stuff inside of the table, is the cumulative area up until that point under the normal curve, the normal PDF, or the bell curve shaped thing. So we can use that information to find out how many standard deviations include C% of the area under the curve using that table or stata. And again, that's because the number of standard deviations on the standard normal, or the size of one, it's normalized to be 1. So these are kind of like standard deviation units on the x-axis. Also, there's z-scores. So our sampling distribution actually has mu and sigma that are not 0 and 1, respectively. So we have a sampling distribution that's normal, but it's just not the standard normal. So what we do is we multiply the number of standard deviations z star or z sub c. They mean the same thing. I think z sub c is clearer, but z star is kind of the convention. It's a critical value in either case. So it's some number of standard deviations we care about by the actual size of the standard deviation of our sampling distribution, which is sigma over the square root of n, and it's known as the standard error. Then we just add and subtract that to our estimate x bar, and we get the following formula. And this formula should capture then C% of the time. We only do it once, so we just need to keep in mind that the procedure has a long run probability of working 95% of the time, or 90% or 99%. So this formula will capture that true parameter in its boundaries, some C% of the time. So that leads us to the following recipe. You don't need to always invoke the theory explicitly, but sometimes it's useful to just, think, why do we actually do this, right? So you pick some level of confidence C, 95% is standard, even if it's arbitrary. You find out the number of standard deviations from the mean, whose area under the curve is C. You multiply this critical value by the standard error to find the range of actual values that enclose this area under the curve on the range of our variable. And then you add and subtract the resulting number, which we call the margin of error, to our estimate to get that range. So here's a quick example. Let's say we want a plausible range of values for the population mean number of grandparents born outside the United States. First, we pick a level of confidence C. Then we'll find out the number of standard deviations from the mean associated with C. We multiply the critical value by the standard error, sigma over square root of n. Then we'll add and subtract the resulting number, which we call the margin of error, to our estimate. So remember that we can just kind of visualize this general kind of standard normal curve here. What we're doing is saying what would be true in general, right? What number of standard deviations generally captures 99% of the area under the curve. So we'll pick 99% in this case for some variety. We don't know the true mean mu, right? But we do know the distribution of sample means about it. So if we add and subtract the number of standard deviations that encloses 99% of the sampling distribution, multiplied by the size of the standard deviation on this sampling distribution, we have a 99% probability before we do that procedure of capturing mu somewhere in there. So how do we find that number of standard deviations? Here it's given in the figure, but how could I find it? You could go to table A or use display inverse norm. The critical value Z is the value that has 1/2 the complement of C to one side. So the complement of C in this case is 0.01, because we want 99% of the area under the curve to be within these two boundaries, so 1% outside. And then we say, well, if we want 1% outside total, we want 0.005 on one side or the other. You could either do the process of finding 0.005 on the left-hand side of the table, or 0.9950 on the right-hand side. Here we go and find 0.9950 in here somewhere. And if we look and see, okay, it's right between these two values here. So 2.57 and change. So we'll just basically round and say 2.575. At this point going forward, we don't necessarily need to be like super precise doing this by hand, because we'll mostly use the computer for this. By the way, I'll show how to do that in Stata really quickly too. So let's pull up in Stata. So let's say display inverse norm 0.005. And you can see that we get this number here. The additive inverse of that, 2.575. It really should be 2.576, but you get the idea. We would round and get the same thing that we got by hand. So now we multiply the critical value by the standard error. So assuming for now that sigma is equal to s and we know this, we would then say, okay, that's equal to 1.63. That was just given by the data. N was 2214. That's also just given by the data. So what's our margin of error then? The margin of error would be the number of standard deviations, 2.575, multiplied by the size of the standard deviation on the sampling distribution, which is this quantity here. That happens to work out to be 0.0892, which is yet another case of the standard error being about this size. That's not terribly surprising since we're working with data from the GSS, so the ends are all pretty similar. And we've been working with some familiar kind of discrete data with standard deviations in the sample between 1 and 2. So it's not terribly surprising that these are all coming up pretty similar. Although this is, I think, the third example in a row where that's been true. So then we would look at our actual CI. So we obtain 1.18, the mean of the sample, minus 0.0892, and 1.18 plus 0.0892. We get 1.09 to 1.27, and that's represented here in the figure. So what this is showing us is basically a variety of different options. We don't know which of these is true, but all of these would be plausible under the null, not under the null, but all of these would be plausible situations. So we kind of use the fact that 99% of the time we'll be within about 2.58 standard deviations of the mean on a normal curve to say, okay, unless we have a really strange situation, we'll be somewhere where a value like 1.24 or 1.17 or 1.20 or 1.23 would be plausible. And this is what those situations look like. So we don't know which of these is true, but that's kind of what you want to envision. Any of them would be captured by our confidence interval. Here's some important advanced facts about confidence intervals. So the standard error, and thus the margin of error, decreases as n increases. To see why, you can think about the arithmetic of the formula. So a confidence interval with confidence c is equal to this. Note that if you increase n, the denominator gets bigger, the entire standard error, and thus the margin of error gets smaller, all else equal. Second fact, there's a trade-off between confidence and precision. So confidence is represented by z, and precision is represented by the size of the overall range. So if we want to be more confident and say, well, we definitely captured the parameter in here somewhere, almost certainly, we would need to blow z up very big. But the precision would suffer as a result because the entire interval gets larger. That's pretty intuitive. So arithmetically that's the case, but intuitively, the more certain you are about some range of outcomes for a probabilistic event, the looser your claim is just going to have to be. A couple more caveats. Unfortunately, some of this stuff is pretty tricky, so there's a whole lot of caveating going on. First, there's this ubiquitous mistake that the confidence interval gives the bounds for 95% or 99%, etc., of all possible sample statistics. Why is that false? It's false because although the margin of error is the correct size, it would need to be centered on the true mean, which we don't know, we're trying to guess it, for that to be true. So for instance, let's say we got a really weird mean. Let's say we got a mean that's 3 standard deviations away from the true population mean. So a sample mean is 3 standard deviations away from the true population mean. We just happen to get a really weird sample. It's going to happen. So in that case, when we calculate our confidence interval and we add and subtract it to that sample mean, that's for sure not going to capture the center 95% of the sampling distribution, just by definition. What it did do, although it didn't actually work exactly in this case, but what it had was a 95% probability of capturing the true population mean. It happened not to, but even if it had, even if we had been just, 1.5 standard deviations above the mean, so still pretty weird event, all things considered, that's still not the middle 95% of the sampling distribution. So the correct interpretation is that this procedure has the population parameters somewhere in a given range 95% of the time, or informally fine, we're 95% confident that the true parameter is within the lower bound and the upper bound. And this is an example, right? So this is yet another simulation. This is one our book shows. Note that in this case, if you happen to get this sample mean here and calculated your CI, that does not give you the bounds for 95% of all possible sample statistics right here. These are the bounds, but this presumes that we know mu. So another way to see this too is that this statement here is not probabilistic, it's deterministic. It says that the samples have this kind of probabilistic quality, that they will be sort of unknown and variable, but that we happen to know exactly what that variability will look like. And unfortunately, a tricky part about a confidence interval is that we simply don't know that. That's another layer of uncertainty. So on that note that there are two layers of uncertainty in a CI. Our sample mean might just be really weird, and our confidence interval fails to capture the parameter. But even if our sample is not especially atypical, the boundaries of a confidence interval are arranged. They're not an exact number, and they're somewhat arbitrary, right? So we have to select our z sub c, and there's no, necessarily correct way to do that. There's just additional ways of doing so.
So let's review hypothesis tests. Remember that hypothesis tests, like confidence intervals, allow us to quantify uncertainty. They let us test contentious claims. Specifically, they tell us how weird our data would be for some contentious claim about a possible value of the parameter. Remember that the parameter is the thing that we're trying to estimate. It's the unknown quantity that matters to us. The null hypothesis states the value of this hypothetical parameter. It's usually a straw person, which is kind of a unique feature of statistical inference that is sometimes a little bit confusing at first, but think about it very much like it is a sort of claim in a criminal court, right? That someone is innocent until proven guilty. We're trying to basically stack up circumstantial evidence against this person. Very much like in a criminal court, in criminal courts, this is maybe kind of a sociological point that might be worth making. There's really not a concept of sort of like complete and irrefutable proof. And indeed, in science generally, we just don't say that we ever prove things irrefutably. One, that type of claim has a bad track record. Plenty of things have been proven beyond a reasonable doubt and then shown to be false. Two, there's always the problem that there's something that you're not considering. So even if it seems like someone is able to say, well, A, B, and C are necessary and sufficient conditions for claim Z to be true, I observe A, B, and C, therefore claim Z. But there's nothing guaranteeing that you haven't forgotten about some other factors, alpha, beta, gamma. And there's really no possible way, and this is actually an interesting philosophical question, but there's really no way to ever be confident that you've excluded all of the relevant conditions. There's a well-known phrase in American politics, unknown unknowns, that's often attributed to Donald Rumsfeld. And I don't have a lot of sympathy for Mr. Rumsfeld, but I will say that that's quite a helpful bit of terminology that I find myself often reaching for. When we know what we don't know, when we're aware of kind of the scope of our lack of knowledge, it's usually pretty easy to deal with that. But the problem is we can never really be completely sure what it is that we don't know, in fact, and that's where we get into trouble. So all we can really do is say, well, based on our knowledge of the case, we think that, as far as we can tell, this would be a very unlikely circumstance if the null were true. But that's a different sort of thing than saying this definitively shows that the null is false, or especially definitively shows that the alternative is true. And another way to think about it that I can't remember which of the founding fathers of frequentist statistics said this, but someone basically made the point that it's a little bit like if you were at a dice game or something like that, or a card game, and you observe someone having incredible luck, right? It's not like you may be totally unable to ever prove that they were cheating, right? It might be the case that the evidence could be, like the hard evidence could be burned, or it could just be the case that they have someone sticking around observing the game and helping them out in a clandestine way. You can't ever actually prove that, right? The point is that to make a relevant decision about, say, whether that person, and maybe you don't even, you're not even going to try to say that they definitively cheated. What you're going to try to do is to say, well, maybe this person shouldn't be allowed into the next game. And to make that kind of decision, you are basically going to kind of use the surprisingness of their performance based on what you would expect to kind of make that decision. But that's different than saying that you have definitive hard evidence that the person cheated. It may simply be impossible to pile it up. So anyways, that's kind of a long aside, but since we are reviewing these ideas, I thought it might merit some further commentary. So the null hypothesis is typically a straw person, such as, person A did not cheat in the dice game. So to construct a hypothesis test, we need to figure out how surprising those data are. And in order to do that, we're going to form a z-score from our data. And this gives us a score taken from the standard normal probability density function. And although it's difficult to actually take areas under the curve of that by hand, we have a handy table. People have gone to that hard work for us in the past. And so we don't need to bother with any of the fancy multivariate calculus. We can just look the values up in the table, and those give us probabilities under the null. So they give us probabilities conditional on the null being true. If we get a low probability conditional on the null, that means that we're surprised by our data given the null. And therefore, what we do is we reject the null. So this z-score here looks very much like the z-scores that we took at the start of this class, but there's a couple of differences. In fact, all three components differ, but they're visibly similar to what we saw before. The actual statistic is a sample mean, so x becomes x bar. The value of the true population mean, mu, is now hypothetical, so it gets a subscript 0. We pronounce that mu naught. And the standard deviation is the standard deviation of a sampling distribution, which happens to be closely related to the standard deviation for the variable itself, but it's actually much smaller. It's sigma over the square root of n. So it's smaller by a factor of root n. It's directly related to the sample size, or not directly. It's actually kind of indirect because it's a root, but you get the idea. It's monotonically related to the sample size, let's say. So then if our sample is sufficiently weird, we reject the null. Again, weirdness is relative to some user-selected cutoff p-value. Remember that we're just calling probabilities p-values now. That's kind of a silly thing, but that's a new bit. So it's relative to some cutoff p-value alpha. We typically use the cutoff of 0.05, which corresponds to the confidence level of 95%, and is relative to the direction of the test. And that's something that's not really a component piece of confidence intervals. One note on hypothesis tests and in general, test statistics as well. These become very useful when you get into higher level statistics and not everything can be cast as a confidence interval, but it may seem in the interim as though we are just taking the long way around doing a confidence interval, which is true. And that's actually how I kind of showed the connection between these things. I showed a proof that you can get the bounds of a confidence interval by simply unraveling the z-score, basically. So you multiply by this quantity, then you add this quantity, and boom, you actually at that point, if you use, instead of the actual empirical z, some critical z, then that is like the critical z that corresponds to some alpha, that just is a confidence interval at that point. You have z star times the standard error plus the observed mean here. You would move over the x bar, pardon me, but the same idea basically. Then what you're doing is seeing, does that include some mu naught or not? So confidence intervals can be easily used to test claims about null hypotheses, claims about the true population mean. Later on, we'll see that, when we get to t statistics and f statistics and chi-square statistics, that those are hard to cast as confidence intervals. They're much easier to treat as basically test statistics. Okay, so here's the actual recipe. Remember that, these don't include the theory. You should understand the theory, but basically to run through this really quickly, we write down a null hypothesis. The null, David and I actually had a good discussion of this after class the other day. You can come up with nulls that are not equalities, but that's pretty complex. And many of the great statisticians who pioneered this stuff actually did not even recognize that was possible. So we're going to keep it simpler than going beyond the boundaries of the founding fathers here. And we're going to say it's always got to be an equality. And the reason is that we have to fix the sampling distribution under the null. It gets tricky when you can't do that. Then you need to write down an alternative. Basically, the significance of the alternative is simply that you're specifying the direction or the region of the sampling distribution in which you'll look. It can be any of the following three: that mu is not equal to mu naught, that mu is greater than mu naught, or that mu is less than mu naught. And then you need an alpha, the cutoff probability. Then you picture the sampling distribution if the null is true. So you just draw a normal curve, you center it at mu naught. It's got the standard deviation sigma over root n. Then you can draw the sample statistic in there and then convert that to the standard normal. So compute the test statistic. Then find the p-value. Basically, all you want to do now is find the probability associated with the z-score. The alternative hypothesis tells you whether you look just in that tail or whether you double it. And then, I just said all this out loud. This is like the very formal way of saying it. So if your alternative hypothesis is that mu is greater than mu naught or less than mu naught, then respectively, you would just find the probability of a z-score greater than the one you found or less than the one you found. If your alternative, as will be most common, is simply that they're not equal, you look in both directions. This is a fancy way of saying double the p-value that you get, assuming that you are taking the p-value that's associated with the tail. So whether or not you'll use the cumulative distribution function directly, like use table A directly, or you'll take 1 minus the value in there, is going to depend on the context. I could come up with a set of rules for that, but I found that starts to get really labyrinthine, and it's just easier to like use your common sense. So you want to look in the tail. You don't want to find the area, like a giant fat area under the curve to the left of it. Almost always your p-value should be something less than 50%, basically. But when you have little evidence against the null, it'll often be quite close to 50%. Although, you do have, I shouldn't maybe say that quite so generally. It's really hard to generalize. I would say, yeah, let's actually just, use that as a rough guide, but it's actually quite hard to generalize about that. But I feel like I want to give some intuition there, but it's actually quite hard to. Okay, so then we compare this p-value to alpha. We just evaluate whether or not the probability that we find is less than or larger than the cutoff p-value that we found before, and then we make a decision. Okay, so let's use this example that I came up with. Again, using the Detroit area study, we're gonna, laughing at my own joke like a complete fool. So anyways, we're gonna use the Detroit area study 1960 wave, which asks people a lot of different questions, but one of them is how many close friends do you have? So let's test the claim, the null hypothesis. The mean number of friends for people that responded to this study in 1960 was 10, against the alternative that it was less than 10. So this is a one-tail test, and we're going to use a cutoff of 0.1, just to vary it. 0.1 is a pretty common cutoff. And here is 678. Our X bar, our empirical sample mean, is 9.59, so a little bit below 10. And our sample standard deviation, which we'll use to estimate sigma, is 11.54. Now, as soon as our next lecture, we're going to be able to say, we'll still use S to estimate sigma. We're going to pay a penalty for it, basically. Penalty is that we don't get to use a normal curve for the sampling distribution. We have to use one that's a little bit fatter and a little bit like, it's got more variation baked in. We'll come to that soon enough. It doesn't actually change what we do in practice until you look up p-values, so it doesn't make a huge difference. So we calculate our test statistic. We'll calculate this in the same exact way when we use t-distributions. But for now, we calculate a z-score. So try this at home. I'm going to just skip right to the answer. So because we've done this a million times. So this is your z-score here. You get negative 0.93. The probability that z is less than 0.93. And remember, our alternative was that we are looking in the left-hand side of the sampling distribution because it was an alternative that the true mean was less than mu naught. So we just get the immediate p-value from a table A or a cumulative distribution function such as that of Stata. Here we get 0.1761. I can show how to do that in Stata really quickly. Let's pull up Stata. So we'll say display normal. I already forgot 0.93, negative 0.93. And we get 0.1761 here. We could also do this with the online stat book, and I show the results here. The link is somewhere earlier in the slides. But basically, we could look at either the standardized sampling distribution, this one here, sorry, the unstandardized, pardon me, or the standardized one here. Note that these correspond to the exact same thing. The reason that we standardize is that this kind of calculator where you could immediately just put in arbitrary mean and standard deviation and then use that to find the p-value is pretty new. Historically, a much easier transformation was just to use the standard score. So we do that here. I rounded a little bit weirdly here. I don't know why. I took the screenshot like 2 years ago. So I might have made a bad decision rounding somewhere, but this basically, comes to the same thing. I know I made a big fuss about rounding earlier in the semester. At this point, it's not as important because we're kind of focusing more on some tricky conceptual stuff, but it is a good lesson to learn. Okay. So thought question, because some of this can be a little bit tricky. So our p-value is 0.17 and p over 2 is 0.0868. Should we reject the null using a two-sided test? The answer is actually no. So we should double the p-value if we convert it to a two-tailed test, which results in these figures here. And what these tell us is that the probability of sample statistics this extreme or more under the null is actually quite large. It should happen about 35% of the time, but just through random sampling error, we would see something at least this weird or weirder, where weird means this far away from the mean in the negative direction or correspondingly far away in the positive direction. So we can't really say much about this in this situation. We don't really have a lot of evidence against the null. Now, we never accept the null. We sometimes retain it, so we simply fail to reject it. But basically, this is just an inconclusive test. That's one way to think about it. Remember some complications of one-sided tests, too. So note that there is this zone of ambiguity here. In the original lecture where this graphic comes from, remember that we had found a z-score for a two-sided test, or the critical z for a two-sided test with alpha of 0.05 is 1.96, right? Corresponding to a confidence level of 95%. That's also our critical z. What that means is that a z-score of 1.96 has basically 2.5% of the area under the curve to the right of it, and then negative 1.96 has 2.5% of the area under the curve to the left of it. So together, that critical value plus or minus 1.96, or that pair of critical values, corresponds to 5% of the area under the curve between the two, and then 95, pardon me, between the two, and then 5% outside. So the problem, though, is that if we're retaining the same alpha, but then we are not actually doing a two-tailed test, but a one-tailed test, then our z-score becomes much smaller. It's a less rigorous test. We actually only have negative 1.64 for our critical z in that case of a one-tailed test, because that has 5% of the area under the curve to the left of it, and then 5% of the area under the curve to the right of 1.64, right? So what that means is that we can sometimes have situations where it entirely depends on the directionality of the test. And we see in this case that a particular z, like the one that we found in this instance, negative 1.875, pardon me, is insignificant by this criterion. So another way to see that is that you double your p-value and you get 0.06. So that's one thing to just be aware of. That means that they can also disagree with confidence intervals. So we've kind of been over that. That's pretty intuitive. You can also do the wrong direction for a one-tailed test. So even though you can see here visually, like if we had said, oh, my alternative hypothesis, pardon me, is that mu is actually greater than whatever the null was here. This is standardized form, so I can't recall, but that it was greater than the null hypothesis mean. That would mean in this particular case, calculating a very large p-value here that's much larger than the rejection region. And the problem is that when we do this one-tailed test, we actually don't get to go back and say, oh, I actually meant the lower side. So in this particular case, if we had an alpha of like 0.1, doing a two-tailed test, we would reject the null, but doing a one-tailed test, we would not. And one thing that's a little bit tricky about all of this is that we have the data right. So it's very tempting to go back and look and say, well, I really meant the other way, but that actually is a form of p-hacking and you should avoid it. Now, you could argue that that's like an awkward and arbitrary part of frequentist statistics. Pardon me, I've been talking a lot today, so I'm kind of garbling my words. And it is. But that said, we can't just change that by fiat. So don't do that. And then here's a bunch of the caveats summed up. We've been over this before, and I said most of this out loud. Some general caveats about hypothesis tests. We never accept the null. We fail to find evidence against it. And the point is that we likely didn't get the population mean in our sample. So even if our results aren't compatible with an alternative, they're consistent with values that aren't the null. So that means we don't ever just say the null is true. Recall also, I think I stress this pretty strongly. So if this seems obvious to you, don't worry about it, because I am pretty keen on writing out exactly what p-values are, but many times people don't write out exactly what p-values are, and then this can get confusing. So remember that p-values are not the following. They are not probabilities that the null is true, right? They might seem like it, but they're actually the inverse of that. They're also not probabilities that the alternative is true either. They are conditional probabilities of observing our sample mean or one's more extreme given the null. And that's broad enough to cover all kind of tailed tests, one in either direction or a two-tailed test. They are probabilities of data this extreme or more given H naught. That's the generic form. It's extremely important to keep this in mind, because otherwise you get tangled in a hopeless mess. And it's kind of weird, right? Because it's indirect evidence about the null. We want the probability of this. We don't have it, though. This is the probability of data conditional on this. And we do like a little tiny bit of fudging to basically make claims about this, but we don't actually have direct evidence about this for complicated reasons. But basically, we would need to know, according to Bayes' theorem, a lot more information than we do to actually directly comment on this. That's the idea. Generally speaking, we'll prefer confidence intervals at this point, since they communicate basically the same information, but there are some situations, as alluded to before, where test statistics are by far easier to calculate. So that'll just depend on context. And that's all I have for this review. Thank you for watching.